did some example, and at the end we did a calculation of power factor using magnitude of P and magnitude of S, and will give us the power factor value as well as the characteristic of power factor. We will continue our lesson in this session, and in the second part of our session we will have a look at our tutorials, or maybe exercise lah for you guys. All right, I'll try to keep this one as fast as possible, and later on maybe you get better understanding where I try to explain the example. All right, for RC circuit, consider we have resistor connected in series with capacitor, and of course to calculate current, we try to use Ohm's law. Here Ohm's law says that V equals to I times Z. Okay, and if you try to calculate the current, V divided by Z will give. However, if you look here, Z is given by the combination of resistor and also minus your reactance value, which is a capacitive reactance value. So here we're going to have R minus JXC. So if you come across with this kind of loads or this kind of circuit arrangement, first of all, have a look at the value of capacitor over here. If it is in farad, you need to find what is the frequency, and also try to calculate what is its reactance value, is Ohm's law. All right, I think we did this one in previous lesson. So using Ohm's law, we can find I, the current, and the current over here. Based on the current, we can say that the characteristic of or the relation between the voltage and the current in RC circuit is given by this term, which is the current is always lead the voltage. And if you remember, recall back what we learned before this, based on this word CIVIL, and we focus on this part, C for capacitor, I will always lead voltage, or you can always put it as voltage lags current in this way. But this is the typical or frequent definition that you found in your textbook. Maybe this also is optional definition, but both are correct in technical. All right, now we are focusing on the power. We did what we did earlier is we try to find the current, and the current should be always lead the voltage by a certain degree, depends on the load. And for the power here, see, we will use the same equation that we found earlier in the lesson. So for P, it's given by VI cos theta, and P in this case will always be a positive value, because cos negative theta negative always give us a positive value, so P should be a positive value. However, for reactive power, sine negative angle, sine of a negative angle will give us a negative value, and of course Q in this case will be a negative value as well. If you try to calculate P and Q in different way, you can always use this equation, and I think I've explained why we didn't put V squared over R. V squared over R, and in this case we put V squared over Z. V squared over XC. why we didn't put this one, because it's very dangerous. I mean, not dangerous in terms of you could blow up your system. No, it's you might did some mistake over here, because the V that we are considering here is the voltage across the resistor. If you have a circuit like this, okay, the V that we are considering over here is the voltage across this element only, okay, here, okay, and the voltage here should be the voltage across the capacitor. So to be used like this. So it's very for beginners, it's very confusing, or sometimes the tendance is very high over here. So that's why we put it as I squared over I squared R and I squared XC, because we know that in series connected circuit, the current will be the same current as you've seen from the source or seen from flowing through the elements. So this is safer in terms of mistake point of view. All right. Okay, once you calculate P and Q, you can combine P and Q in order for you to get what is the complex power of your circuit. And the complex power over here is given by S plus P equals to P minus JQ. And remember that Q will be always the imaginary part, and P always it's the real part of our complex power. So sometimes this active power also named as a real power, but this reactive power never known as imaginary power. Normally we will say it like this. For reactive power, it's a reactive power, VAS or VAS. And the reactive power of capacitive circuit here is very important. It's always negative. So you need to be aware that if you have a capacitive circuit or a capacitive characteristic circuit, capacitive characteristic load inside your circuit, so your reactive power should be a negative value. And in terms of over here, you see that P and Q can be calculated this way. We have also another way to calculate our power for RC circuit, actually power in AC circuit. We can simply use S equals to VI conjugate in order for us to calculate our complex power. And once you done with the multiplication, including the conjugate value of current, you will get complex power magnitude and also complex power angle. And the magnitude here actually is our apparent power. Apparent. Apparent power, or sometimes labeled as S, the magnitude of S. This is not absolute, this is magnitude of a vector. The magnitude of your complex power, also known as apparent power, and if you convert it into a rectangular form, the real part is basically your active power, real or active power, and the imaginary part, IMA, IMG. Imaginary part is your reactive power. And please note that for RC circuit, we will have a negative value of reactive power. Negative. Okay, this is for RC circuit. And towards the end, if you've been asked about power factor, you can use this formula, okay, cos theta. And the most important thing is that for power factor for RC circuit, it is a leading power factor. So this is very important in order for you to get a full information of your power factor. I mean, to give full information of the power factor. And apart from using this cos theta, you may use also for power factor, you can use P, okay, the value of P divided with the value of your apparent power, P divided by S, or you can also use this one, cos theta, but the theta over here, you use theta Z. Actually, theta Z is the same as, theta Z over here is the same as theta V minus theta I. Doesn't matter. And maybe later on I put it in example. I explain example. Okay, we proceed with example. If we have a series resistance and a capacitance of 10 microfarad applied with 100 volt, 300 hertz. Okay, remember here that this voltage value is presented or is given in not in a sinusoidal form. Means that this value is the VRMS. Okay, and this of course the frequency. Okay, and you need to calculate the current and the phase angle. So to calculate the current and the phase angle, what you need to do, you need to have this impedance information. And since if we draw back the circuit given by this kind of connection, we have resistor over here, we have GXC, and supposed to be a minus JXC, and the Z is given by R minus JXC in this case. So if you look at the calculation to get the current value, we will use Ohm's law where V divided by Z, and we will get this value. Okay, the one that we see over here is our theta I. Okay, and since the voltage, we don't have any information on the voltage angle, we can assume that this voltage angle is given by 0 degrees. So this is the theta V. And earlier, when we try to calculate our Z, we come across with the rectangular form of Z. We have 47 minus, this is R value, minus JXC value. And if you convert from rectangular to a polar value, okay, this part is known as our theta Z. Okay, and this one is our Z magnitude of Z. And I think magnitude of Z is not quite significant compared to the usage of theta Z. Where if you look at the next, in question number 3, when we try to calculate power factor, this theta Z is quite useful in our calculation. All right. Anyway, we try to go one by one. The first one, I think it's settled with the current value, and the current phase angle is given by 48 degrees. And since this is RC circuit, here we have a current leading the voltage about. All right, for the power in this circuit, the fastest way to calculate the power is by using this equation. Because by using this equation, we will get all information of power. We will have your, you will get your complex power, you will get your value of real power or active power, as well as your value of the value of reactive power. So the thing that very important using this using this equation is by considering the current over here is a conjugate current. So voltage, I think it's quite straightforward. However, for the current, since you have current you calculate earlier is 1.4 with an angle of 48, to get a conjugate value of the current, you just add negative value. So negative over here will get you the conjugate value of your current. Okay, and when you multiply voltage and the conjugate current, you will get your complex number given in a polar form. And in order for you to get to know what is your active power as well as reactive power, it is good that you convert this polar form into a rectangular form. When you convert this polar form into a rectangular form, the real part over here will give you your active power value, and the imaginary part here, I would consider all the, including the sign of the imaginary part. Okay, this will give you the value of your reactive power. So it's very easy, I mean convenient, fast, and easy to use if you try to calculate all the power information using this equation. So now we will have your, you will have your apparent power. This is apparent power, which is given by 140 VA. Your active power given by this portion, which is 93.7 watt. And your reactive power, make sure if you try to write your reactive power, please include the sign of your reactive power, because the sign is very important in order for you to get to know the characteristic of your load impedance as well as your power factor later on. So now your, I know maybe some of you would argue, hey, this one is absolute, why you must include negative? Please remember, this one is not absolute. This is the magnitude, means the magnitude of your powers. And later on, if you try to calculate power factor, we are in question number 3 now. So when you try to calculate your power factor, the fastest way, I believe, by using this equation, because we do have the power information of P and also your apparent power. Just divide those two. But the most important, I mean, another important thing that you also need to know is that the power factor must come with its characteristic. So here, since the current leading the voltage as well as the nature of the circuit itself is an RC circuit, so your power factor should be a leading power factor. If you try to calculate power factor in different way, what are the options that you have? The option that you have, you can use like power factor equals to cos theta Z. Okay. You may also use this one because of why? If you put it in a calculator, cos 48 it also gives the same answer, 0.669 or 0.67, the value of your power factor. And the characteristic, you just put it's as leading power factor. So you can use either way. Maybe some of you guys prefer this one, or maybe prefer this using this formula. Both will give you the same answer. All right, that's for example RC circuit. So basically this is not exercise. I would say I would like to give you the solution over here. Later on, maybe we can get into the exercise. This kind of question is the typical question you've seen in your assessment. We're gonna have parallel connected AC circuit, and from here we try to calculate what is the current, what is the powers, as well as the power factor. So according to this question, if we go through, okay, the first one is that the voltage here is given in sinusoid form. So 240 you've seen over here is its maximum value or its peak value. So what I suggest is that this value should be rewritten in its RMS value. So VRMS equals to 240 divided by, very important. And if you look at the equation of the voltage, over here, it's your theta V. So VRMS also comes with its angle, which is 30 degrees over here. Right, now the last information that we can capture from the voltage equation is this part. That is the information of our omega, where omega here is given by 2 okay, omega is given by 2 pi times frequency. So from here you can extract what is the value of your frequency if required. And looking at the question, the frequency of the system is given by 50 hertz. Basically, this 50 hertz is, that 50 hertz is coming from this equation as well as this value. So sometimes this frequency value is not given in your question, but the option that you have in order to capture what is a frequency value is by looking at the equation of your voltage or your current, your source in general. Okay, that's about the voltage source. And in your circuit, if you go through the connection, inductors and also capacitors are given in its real value, in its original value. So what you need to do is you need to convert this one into its its reactance value. So for inductor, you will get GXL, and for capacitor, you will have negative J XC. And in general, this branch is R plus GXL for this branch. Okay. For the other branches, R minus GXC. This is for this one. Okay, and that is what happen in our circuit. So we get into the question in detail. Here it says figure shows an AC consists of two parallel connected branches. Calculate the reactance of the inductor and capacitor. So what you need to calculate is you need to calculate XL and hence find the total impedance in the circuit. So total impedance over here is ZT, Z total impedance. And total impedance is by looking from the source. Okay, because from this total impedance, we can easily calculate what is the total current inside our circuit. All right, for question B, determine current I2 and I3. I2 is the current flowing through this branch that consists R plus JXL. And for I3 is the current flowing through this branch, the second branch, consists of R minus JXC as our impedance. So to calculate I2 and I3, maybe you will try to use methods like current divider rule, or maybe other option if you like. But I think the easiest way or the fastest way to calculate I2 and I3 is by using current divider rule, and later on maybe using Kirchhoff current law to do that. And lastly, we need to analyze the total power of the circuit, where we need to calculate what is active, reactive, parent power. So means here the question asks about total power, means we need to use voltage, total voltage source, and also total current, okay, in the circuit. So let's have a look at its answer, the answer of this exercise. Where is it? Exercise here. Okay. This is what happened in the solution. Okay, the first one, can you see it now? Clear? Is it clear?
Yes, quite clear.
Yes, Doctor.
Okay. All right, thank you. All right, this is what I mentioned earlier about the how do we analyze, basically scan through the question. The first one is about the voltage. Voltage should be, in this case, is given in sinusoid form. So we need to convert it into frequency domain form or polar form. So now we have VRMS with the angle of 30 degrees. And it is a good idea if you give both value, both in phasor as well as in rectangular form. And this is also mentioned just now about the omega, and from the omega we can get our frequency value. And according to the question, first we need to calculate our reactance or inductor, XL. So to calculate XL is given by G omega L. Omega is given in question as 100 pi. We just put it there. We multiply with the value of our inductor and we will get XL value. And for reactance associated with the capacitor, so we have negative JXC over here. So using this equation where negative JXC is given by negative J times 1 over omega C. So XC basically is 1 over omega C. Solving this, all the parameters over here, you will get your negative JXC as negative 159.2 J. Negative J 159.2 ohms. All right. As I mentioned earlier also, it's about the branches. The first branch is, here I simplify the branches as ZA. So ZA is R2 plus JXL. I know the resistor is not being labeled as R1, R2 or R3. You can also label it yourself to make your calculation looks nicer or easy for you to calculate your circuit. Now, ZA is given by 80 plus J31.4. That is for the first branch. For the second branch, I label it as ZB. ZB is 20 minus J159.2 ohms. And looking, since our main target is to find what is the total impedance. The total impedance over here, this is our end goal. We try to find the total Z or total impedance. Looking at this circuit arrangement means that these two is in parallel. These two is in parallel. So that's why I have a parallel connection calculation, parallel connected calculations over here. ZA in parallel with ZB. So ZA times ZB divided by ZA plus ZB. And at the end, I will have my ZC over here, combination of ZA and ZB. And to simplify, to get my end result or an answer for ZT is given by R1 plus ZC, and because this is considered a series connected connection between R1 and ZC, so that's why we have a plus over here. Okay, I think if you do it step by step and you simplify your circuit step by step, you will find it is easy for you to trace your calculation, where is the mistake in your calculation, and so on. So please, if you look at my solution, I expect that you will try to, in your solution, your explanation to the examiner should be something that looks like this. It's easy for people to get to know what is going on in your solution. All right, that is for our Z total. And remember that in question number B, or question B, we try to determine the current I2 and I3. And here, to calculate I2 and I3, we need to know what is the information of I total. So here, I total is basically current over here. Is also I1, given by I1, and can be calculated by using the simple Ohm's law, V divided by Z total that we found earlier. So now this current is known, and to calculate the current in each branch, the best way is by using current divider rule. Using current divider rule, for example, if I try to calculate I2, I take the impedance value of the other branch divided by the summation of those two branches. Maybe this is a basic knowledge for you guys. We learned before this in before semester breaks in DC circuit. This is the same using current divider rule. All right, I2 is given by this equation, ZB divided by ZA plus ZB times I total, because we know that the total current is over here. So we try to divide those the total current, and in order for us to get what is I2. So that's the calculation for I2. And you can also use current divider rule to calculate I3, but I think the easiest way or the fastest way is by using KCL. Remember that KCL says that sum of current in equal to sum of current out, and considering this branch, we have current in, which is IT, current out is I2 and I3. Since we have the total current over here, if we minus with the current that we found in for I2, we will simply get I3. Or you can also use current divider rule over here. If you use current divider rule, the equation will be like this. ZA, because we consider the impedance at the other branch, ZA plus ZB, and we multiply it with the total current. Either way, if you prefer this equation, you can use this equation to find I3. But in my solution, I think better I use KCL because I just minus or subtract the total current with the current that I found earlier for I in this circuit, which is I2. So that's for the total current, for the value of I2 and I3. We solve part B. And for the last one is the total power. And total power means that we will use information of our voltage and as well as information of our total current. In this case, the easiest or the fastest way is by using this equation where we have V times I total conjugate. So 169.7 with the angle of 30 degrees times 1.26. Here is the conjugate effect. We have negative of 35.95 degrees. And after that, you will get your complex power value, which is in polar form, as well as you can always convert it into your into a rectangular form. Why we need to convert into rectangular form? Because we know if we have a rectangular form, means that this part will be our P, and the whole part over here, imaginary part, will be our Q. So we don't have to calculate P and Q later on, just by using the value that we found using the conversion from polar to rectangular. And before that, after we finish with the multiplication over here, the magnitude of our vector over here is our apparent power, or the magnitude of S. So here, I just list down all the information that based on this calculation. Apparent power is 214.01 VA, active power 212.9, reactive power negative 22.2 VARs. And I put this one as a capacitive because I have a negative sign for my reactive power. If you don't put this capacitive information, also can, because if you have this sign, negative sign, it is understood that this is a capacitive characteristics of a circuit. All right, to calculate the power factor, the fastest way, I believe the fastest way is by using this equation, because we already calculated our value, we already determined our P and also our S. So just by using that, applying that value in this equation, we will come with the value of our power factor. And please remember that power factor must come with its magnitude, the value of power factor itself, as well as its characteristic. Okay, I think I'm done with the example. And any question before we proceed? Any question?
No, sir.
Okay. Now, as for summary, you can have a look at the summary that I have over here. This is the characteristic, the way we calculate our quantities in AC circuit in terms of its impedance, current, as well as relationship between voltage and current. And later on, you the summary of how to calculate power, PQS, and also power factor. I think you can go through this one, or maybe we will go through this one later on during our revision class. But basically, this is just information for you. It's a summary of what you have been, what you have learned in the second part of your semester. All right, I think that's the end of our session. Not session lah, supposed to be last Tuesday session. And in the next topic, we'll try to have a look at AC power analysis in terms of parallel connected AC network. Basically, we also have a look at parallel connected in this example, but this one is a bit different from what you've seen over here. Maybe it's related to the power information of how do we combine all the power values in parallel connected AC networks, and also how do we determine the power factor of if we have a parallel connected AC network as well. All right, that's for the first part, and as I promised before this, we try to have a tutorial session, and I think I will leave you guys sometimes to complete the tutorial. Maybe about 20 minutes. I think enough, 20 minutes. And another 30 minutes, we try to discuss our solution and also the solution for the rest of the question in tutorial session. All right. Looking at the tutorial over here, can you see the tutorial here? You can find this question in e-learning as well. You can download it later on, or now if you want to download it now also can. Okay, we have two questions in this time. The first one is a bit similar to what we have seen in our exercise. I hope that we try to do this one, because the next one is a bit complicated. It's a bit we have more elements inside our circuit, and maybe we decide to do this question first, and I will try to explain what the solution of this question to later on. Okay, we'll give you guys 15 minutes enough? Is it enough, 15 minutes?
Yes, doctor.
Okay, 15 minutes. And we meet again at 12, 15 minutes from now. 12:25, I think. 12:25. Yeah, 12:25. We will meet again and discuss. And I would really happy if there is a volunteer from you to present your work. Just WhatsApp your work in, post your work in the WhatsApp group. I will try to, we will try to discuss what's going on, how much marks that you, how many marks that you can get from that one. All right, we meet again at 12:25. All right, give you about 15 minutes to answer this one. Okay. The 15 minutes time is up. Any volunteer to share his or her answer, or shall I randomly choose one? Oh, okay. Thank you, Mo. Can. Post your answer in through our WhatsApp group. I'll try to present it here. It's okay, Mo. Maybe up until what you have currently. Maybe later you can finish out the one that you left. Because now already 12:27. We don't have much time because we have one more question to discuss. Okay. Just check the answer. Yes, correct. Okay, this is what we have from Mo. Is it clear enough? Can you see the answer over here?
Yeah, Doctor.
Okay. All right. This is what I have in my solution. Okay. According to the solution that we have from Mo, okay. I just look at the final answer over here. It's the same. So the whole thing is correct. You will have 2 marks over here. Okay, what's happening in this solution where is that when you try to calculate your total impedance, you will try to have a look at the impedance looking from the source. So here we have parallel connected connection of we have 2 branches connected in parallel. So first you need to solve this one first, and later on in series with the inductor that we have before the source. So now Z total is given by J20 plus 30 minus J10 in parallel with 20 plus J60. And to be J20, oh, okay. All right. Something missing over here. Mok say left out 20, J20. Okay, it's okay, Mok. At least from 2 marks over here, you will definitely not gonna get 2 marks lah. But I will consider this one as 1.5 marks. Only miss 1 mark over here, half mark over here. But the worry is that if this part is wrong, means that the whole thing will be wrong as well. So this part is very crucial. Anyway, we try to have a look at what's going on in the solution. So as I mentioned earlier, this part should be combined together. And the best thing is that you don't need to calculate your reactance value using your omega, because the value of the components over here is given in its reactance value, and as well as resistance value. So you don't need to convert from its original, for example, original inductor value and use frequency to get XL. Same goes to XC, using frequency to get XC. Anyway, please make sure that you look all the connection, and over here, the difficult part, it's okay. However, the easy part, you miss out over there. And please note that if you did, if your answer over here is wrong, means that the whole answer over here also wrong. However, if the what do you call it, the flow or the procedure, it's clear, and you just miss out J20 over here, I will consider give marks for the rest of your solution over here, but not a full mark lah. Maybe half mark for your effort. Not half mark. For example, if we have, for example, here we have three marks, I will give you 1.5. If we have 2 marks over here, maybe I will give you 1, because of your effort and your strategy is correct. Just because of your value over here is wrong. Okay, don't worry, but please remember that if in your solution, please give as much information as possible to the examiner so that you can gain mark from there. If you just leave it like that and just put all the numbers, I don't know what is the meaning of this number. For example, here mock says that power factor is P times VI. This is wrong. It's totally wrong. This is, you cannot gain mark from here lah. Power factor is coming from cos theta, or P divided by S, or using cos theta Z. So this is totally wrong. I just saying that if this is correct, but the value over here is wrong, means you will still got mark. However, based on what mock presented over here, I will only consider this one as a mark. Mark can be given only at this part. This one, I think, is totally wrong. The strategy as well as the numbers over here. Okay, thank you so much, Mark, for your brave effort to volunteer. Okay, at least you know what is going on in the solution and how you can improve from your mistake. Okay, right, we've straight into our solution over here. The first one is to get total impedance. As I mentioned just now, the total impedance should be coming from this parallel connected elements. Okay, maybe we have a look at the question back. Okay, these 2 parallel connected elements in series with this J20 ohm. So that's what happened in the solution. And to get here, the total power factor, as I over and over explained to you in the example, as well as the revision that we did in this class, in the first part of this tutorial session. Power factor can be calculated using theta, or the angle of our loads, of our impedance. So here, the total power factor can also be calculated using cos theta Z. So theta z is where? Here, the one that you found earlier in the total impedance. You can use this information to get your power factor. And of course, maybe you were wondering, if I put cos 40.6, I only managed to get this 0.76 value. How about the characteristic of the power factor? Okay, looking at the impedance, if you combine the impedance, you will end up with 28 plus J24. This 28 plus J24 means that you're gonna have an RL circuit, means that the circuit itself is the nature of the circuit is inductive because we have plus J24. If you have minus J24, the nature is capacitive, means we're going to have leading power factor. So here, the nature of the total impedance is inductive because we have plus Jx over here. Actually, the plus here means everything towards the definition characteristic of our power factor. So plus means that our impedance is inductive, means our power factor should be a lagging power factor. So from here you will get 3 marks. And for the second part, calculate the current, active power and reactive power of each parallel branches. Sorry about that. The current, you need to calculate the current of each parallel branch, means that you need to calculate I1 and I2. So the best way is by using current divider rule. So here is the way that we calculate the I1 and I2 using current divider rule. First thing that you need to calculate is the total current over here. And then you will divide the current for I1 and I2 or I2 using current divider rule. According to the solution, we have I total given by V divided by Z total. And for I1, I will use current divider rule. So since I1 is over here, so I need to use current divider rule by using this equation, 20 plus J60 divided by the summation of these two parallel connected branches. So here we have 20 plus J60 divided by 30 minus J10 plus 20 plus J60 times the total current. I would say my my solution over here is not what do you call it? It's not as detailed as I wish, because suppose I try to put the value, the equation first, later on put the value. Here I just put the value. Hopefully you will get the answer or the solution correctly. Okay, now we have I1 using current divider rule, and also I2 using current divider rule as well. For I2, I will consider this branch divided by the summation of both branches, 30 minus J10 divided by 30 minus J10 plus 20 plus J60 times the total current. So I will get my answer for I2 and I1 both using current divider rule. You can also use the strategy that I showed you in the example using Kirchhoff current law as well. All right, now for the powers, we need to calculate active and reactive power. So if you try to use VI conjugate, make sure the voltage that you calculated or the voltage that you use is the voltage across the here, voltage over here, as well as voltage over here. And also Yeah, and because we have this information of I, for example, let's say this is V1 and this is V2. Basically, V1 is equal to V. It is in parallel connected. However, V1 and V2 is not equals to the V over here because we have another voltage drop here. So V1 equals to V2, but not equals to V we seen from the source. So to use VI conjugate, okay, I over here is very straightforward because we have VI1 conjugate, and we can also use VI2 conjugate. Okay. However, the voltage here should be for for the first band should be V1, should be V1. Oh, sorry. This should be V1, and over here should be V2. Okay, that's why in my solution, I not suggesting this kind of strategy or this kind of solution because it's very find V1 and V2 first in order for me to calculate my active power and reactive power. So that's why here I use, although this is actually correct, I use the current information. So to get P, I use I1 squared times R because P only due to this component, okay? And to get the reactive power due to this component, so that's why I have I1 squared times X. And if you use this one, the equation, make sure that I over here is the RMS value only of the current. So according to the calculation that I have earlier for I1, I have a magnitude of 5.82. Don't take this value, because this value is the rectangular value. So this is a real part and imaginary part. To use this formula, you need to convert to polar form and take the magnitude of the polar form to be used over here, and the power our active power can be found using this I1 squared times R, and same goes to Q, but here we will use the information of our reactance. And you only the value, not the signage or the sign of your reactive power. So how do I get this negative? So this negative sign is basically according to the circuit connection or the element itself. The element over here we have capacitor, means that the VAS or the reactive power should be a negative value. So I put it here as a negative VAS. Okay. Now, in some case, if you forgot to put this one, you can always get a full mark over here. However, it's very dangerous if you didn't put the signage of your reactive power, because later on, if you try to combine all the reactive power, this is quite crucial. So please remember, if there is a reactive power, or if you want to give a value of your reactive power, please include the signage as well, so that you will not doing mistake later on in your, for example, if you try to combine all the reactive power. All right, for branch number 2, also I will use the same strategy. Here I will try to use I2, not try, I will use I2. And for active power, we multiply the square of I2 with the resistor. And for reactive power, I will use the reactance value over here. And as I mentioned just now about the signage of our reactive power, this is according to the elements of this in the circuit. Since we have inductor over here, means that the reactive power should be a negative, it should be a positive value. So that's the solution for question number 1. Why don't need VRMS? Oh, okay, good question. Because this one, okay, if you look at the information of the voltage over here, it is presented in polar form, yeah, polar form, or in its frequency domain form. So if being given like this means that this is already an RMS value. Okay, if it is given in, for example, let's say we have V of t 240 sine blah 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 blah. Okay, this one is our maximum value and we need to convert into RMS value. Okay, now did I answer your question, Nathan? Okay, right. For question number 2, if you look at question number 2, it's a bit complex. Not complex, I think tedious work lah, because we have more components inside our circuit. However, we have a look at the solution over here, one by one. If you look, the marks contribute to this question is very substantial over here. We have 20 marks just for this question. In order to get into the question, first we have a look at the information that we have over here. So now information of voltage is given in a rectangular form. So my advice, you need to convert into voltage in a polar form as well. And since it is not given in, it was not given in sinusoid form, you can consider this is the conversion, and later on this value is your RMS value. Doesn't matter. All right. Now get into the question. The first one for total impedance seen from the AC source. Basically, we try to calculate the Z total over here. Okay. I simplify my circuit seen over here. So I have these two JXL and also negative JXC are connected in parallel. Okay, before that, the information, the components inside our circuit were given in its original value. So you need to use the frequency over here in order to calculate the value, reactance value, XL, XC, and so on. Okay, now XL and XC must be calculated, but the most important thing that you need to know, where is the Z total looking from? So the Z total is looking from the source over here. So we have these two. Okay, maybe I put it as comment. Okay, these two should be connected in parallel. That's why here I have ZA equals to the parallel connected of JXL and negative JXC. And later on, I have this R3. I did nothing with this R3, just simplify this one. And in the next figure, I combine R3 and ZA to become ZB. ZB is basically the combination of R3 and ZA, and I will get into parallel connected of R2 and ZB, and I simplify this one, label it as ZC, and at the end combine R1 and ZC as a series connected elements. So that is how I calculate my Z total, and this will give us about 6 marks. And for the second part, we need to solve current IO and voltage VO using source transformation. This is quite tricky because if you look at the connection itself, we have a voltage connected in series with R1, where this part we can convert or we can transform into current in parallel with R1 or in parallel with our impedance. But before we get into that one, you need to also consider that these two connection or XL and XC should be combined first, okay? And this is basically ZA seen from the one that I have over here, which is negative 35.42. And if you look at for ZB, okay, ZB is the combination of ZA and R3. So these two is connected in series. You need to combine that one first, and at the end you will end up with 3 connected elements in parallel with your current that you transform this from voltage into current source. So the transformation is quite straightforward. We just divide voltage and R1 to get our current value, and to calculate IC over here, I will use current divider rule. But here you see that my current divider rule equation is a bit different because I have 3 connected parallel elements. So I need to use this equation where I need to use Z total divided by ZB. However, this Z total is not the same like you seen over here, because Z total for this current divider rule is based on what you see in your part 2 circuit simplification, not the same that you found in the first part. So Z total over here is given by R1 in parallel with R2 and in parallel with ZB. I believe this calculation is quite tedious. Is longer than this. The way we calculate that one. That's why I considering to give marks to student about 2 marks. And this also I will give 2 marks to student because it is not that easy. You will see that my calculation here is very simple. We put Z total divided by ZB, the impedance over here, and multiply with I. But not many students know this. If you have 3 connection, if 3 connected parallel, 3 connected parallel elements, 3 parallel connected elements. Sorry about that. We will consider this one. We will consider this equation. So that's why I also considering about 2 marks over here. So you need to use this formula. Just remember that Z total that you see here is not the same that you found over here. Okay, not the same, because this Z total is given by this equation based on the simplification of this circuit. All right, now I done with the current IC over here, and IC, the current that I calculated label as IC, is basically the current over here. Okay, current over here is IC. And my main objective is to find IO, where I need to perform another current divider rule, where here I have two parallel connected elements and I have a total current over here IC. How do I divide these two current and to get this IO? So that's why I will use current divider rule, and since I have two connected parallel connected elements, so I can use a simple current divider equation, where if I try to find the current over here, I will consider this value divided by the summation of both value times the current coming before the branches. So this is how I find IO, and I get my IO as this value 3.92. And since I have the current value flowing through the elements over here, so it is easy for me to calculate what is the voltage drop across that element. Then this is basically a simple Ohm's law, where I apply a simple Ohm's law to calculate my voltage across GXC, or across the capacitor. So that will give us about 10 marks. And the rest of the marks, or another 4 marks, is apparent active reactive power and the power factor of the circuit. Means that we need to determine what is the total apparent active as well as reactive power, and later on we need also to calculate the power factor. So if we need to find if we try to find the total power, means total current information is very crucial. So that's why here I calculate the total current. Total current given by this value using Ohm's law. I total equals to V divided by Z total, and Z total over here, which Z total I considering? Okay, here Z total is the same that you see over here, the first one, because I did nothing in terms of modifying the circuit. So this is the original circuit, and based on the original circuit, the Z total over here is given in part 1. So I will take the information I calculated in part 1 over here and use that to calculate my total current. And the fastest way, or the easiest way to calculate all the power information, is by using this equation, the complex power equation, using the I total conjugate, the conjugate value of the current. So the conjugate value of current, since I have here current is 14.33 with the angle of 38.82. So the conjugate value here is negative 38.82. And multiply that one, I will get it in polar form. In polar form, remember that this magnitude of our complex power is basically the apparent power. And if we convert into what we call it, a rectangular form, here is the rectangular form, and this part is considered our active power, and the whole of this part is considered as our reactive power. And remember that in this case, the reactive power is a negative value. So looking at the Z total that we calculated earlier, yeah, Z total equals to 13.79 angle of, sorry, not angle. Goodness. Okay, maybe delete this one. Z total. Okay. Looking here, we have R 13.79 minus GX. Okay, minus GX over here give the indication of, okay, my total load over here is a capacitive in nature. Actually, all the load that I have over here can be simplified into this kind of circuit. I have total resistance and I have a capacitor over here. Because based on the Z total that I have some value of real value over here minus JX. So G minus JX means that we have like this and we have R over here. So that's why I have a negative value of my reactive power. I'm sorry because I took a bit longer this time around because I'm just finishing up my solution, yeah. Right now, as I mentioned just now, using this formula, we can easily compute all the information of our powers. The apparent power, active power, as well as our reactive power. I just put all the values over here, and at the end, in order for me to calculate the power factor, I apply this value and also the apparent power value, divide it and get the value of my power factor. And to determine what is the nature or the characteristic of my power factor, I would refer back my reactive power, which is my reactive power gives me the value of negative value. So it means this power factor should be a leading power factor. All right. Any questions so far?
No, sir.
Can you get all the solution? Maybe later on, later on today, I will put it in e-learning so that we can revise it back. I think you might prefer the one with the annotated version. I will put this annotated version in e-learning as well. All right. I think that's all from me today, and I'm really sorry that today we already passed 3 minutes past 1. Sorry for that. Need to use a bit longer time in order to explain all this because we spend sometimes in the first part of our tutorial to complete, to finish out what been left from Tuesday's class. Okay, as usual, please switch on or turn on your camera so that I can take a snapshot of this class. And don't forget to fill out the EPP form because based on the record that I have, so far we have about 76%, around 17 students, not 17, 12 students, something like that. 14 students already answered or fill out the survey. Some of you guys, maybe three, maybe Omer have difficulties to fill out. I understand about his situation, but the rest should you should fill out the form to evaluate this class or this course. Okay, anyway, we'll meet again on Tuesday. Hopefully you can get back on Tuesday. We'll try to finish out our course. That will be our last topic, final topic. It's very short topic, and the rest will be maybe the following week will be our revision session. Okay, with that, again, thank you, Mok, for sharing your answer. And we meet again on Tuesday next week. Assalamualaikum. Very good day and stay